Welcome to Homework Lib.
Okay, so we're doing problem number 21. And it says, consider two antennas separated by 9 meters. Let's write that down. D equals 9 meters that are radiating in phase at a frequency of 120 megahertz. Okay, good. And a receiver is placed 150 meters from both antennas. It measures an intensity of I naught. Okay. Now the receiver is moved so it's 1.8 meters closer to one antenna than to the other. Okay, so to understand what that means, let's draw this here. We have this antenna 1, here's 2, and here's going to be our receiver. So this we're called distance R1. This distance to the receiver from the second antenna we're called R2. So it said that the receiver is moved so that it's 1.8 meters closer to one antenna than the other. So that means the difference in these distances is 1.8 meters. Okay, so now let's go to part A, see what it's asking. It's asking what is the phase difference, phi, between the two radio waves produced by this path difference. Yes, so this is the path difference here. R2 minus R1 is 1.8 meters. And now they were originally in phase. They moved this closer to a different path difference, 1.8 meters, which means they're going to accumulate phase or have a different phase accumulation across the path. And now they're not going to be perfectly in phase, so there will be some interference. And the phase difference in a two-source interference is given as 2 pi over the wavelength of the signal times the path difference, which we already have here. But we need to figure out what the wavelength is. We do know what the frequency is, so we can figure out how those are related. And those are related by the wavelength of a light radio wave, which is light signal, is the speed of light divided by the frequency. Okay, so let's calculate what the wavelength is first. So this is 3 times 10 to the 8 meters per second, which is the speed of light, divided by frequency, which is 120 megahertz. Megahertz is means 10 times 10 to the 6 hertz, so this is the same as 120 times 10 to the 6th hertz is 1 over seconds. So if we see these out, these seconds cancel, we're left over with meters. So if we plug this into our calculator, we will see that our wavelength is 2.5 meters. Cool. So now we can go back into this first equation here to solve for our phase difference. Here we have phi equals 2 pi over our wavelength, and that's 2.5 meters, times path difference, length difference, which is 1.8 meters. Perfect. So we can plug this into our calculator, and we can see that the phase difference is 4.52 radians. Perfect. Okay. So let's move on now to B, see what this is asking here. In terms of I naught, which was the initial intensity, what is the intensity measured by the receiver at its new position? Okay. So we know that the initial intensity I naught is the max because they were both in phase. If they're perfectly in phase, that means they're constructively interfering to their max perfectly. If they're a little bit out of phase, the intensity is going to go down. And in two-source interference, the intensity is given as the max intensity times cosine squared of your phase difference divided by 2. But now our I max is our original intensity, I naught. And now we can plug in our phase difference from part A to figure this out. So our I, in terms of I naught, is going to be I naught times cosine squared. Our phase difference was 4.52 radians over 2. And this, finally, plugging into our calculator one last time, gives our answer of 0.404 and naught. So there's our answer for A, which we use, or there's our answer for A, which we use in finding our answer for B. Perfect.